Right, so in this video we're going to look at energy in simple harmonic motion. Okay, so go back to the standard pendulum. I like a good standard pendulum. We've got our equilibrium point here, amplitude, amplitude. And so, as we said in the previous video about velocities, we know that the velocity here is equal to the maximum possible velocity. And here we've got a minimum velocity, i.e. it's going to be equal to 0 for an instantaneous second. So there are a number of equations that you can use for looking at the energy at different positions along this pendulum. So for some of you these may seem fairly obvious and simple, but for some others it might just take a little bit longer just to get your head around, oh yeah, you can work out the energy at a specific point on this pendulum. So say I want to know what the kinetic energy was at this specific point on this pendulum. Well, we take the kinetic energy formula and we can go, okay, fine. Kinetic energy is equal to a half mv squared. No problems, and that maintains. You've got a mass of a pendulum here, it's going to have a velocity, and we're going to have a kinetic energy here. But there's a problem. What if I don't know the velocity? Well, you could turn around and say, okay, well, yeah, if I don't know the velocity, I could probably have some other information, maybe with the displacement or the time, and I can work out what that velocity is. But it would be much nicer to have an equation that makes sense for it. So let's make an equation for it. So at this point, you'll remember that there's an equation that's V is equal to plus or minus omega x naught squared x squared, where v is the velocity at this displacement with this amplitude. Remember, x naught is amplitude. V omega is, this is a little w here, is omega, it's the angular velocity. So we can actually utilize this equation and actually sub this into here to get a nice equation for this value. So we can say that kinetic energy is equal to a half m omega squared x squared minus x squared. Because we've squared both of these values and we've got this equation, so we've got rid of the square root, but we squared this value right here. And actually what we've come up with now is a nice equation for kinetic energy. So we've got that one. What about the other form of energy that's going on here? So you've got the potential energy. And before we get to potential energy is obviously the potential that it will have to turn into kinetic. Now remember that from this point to the equilibrium, it's swapping from potential to kinetic. Okay, so it's got the max potential at the amplitude and the max kinetic here. So we can actually infer something quite interesting. If all of the energy has been transferred from potential to kinetic at this point, then the total energy in this system must be equal to the kinetic energy at this point. So you've got the max kinetic is equal to the total at the energy at the equilibrium. And we can manipulate this equation now to come up with an equation for that. Because Ke max is going to be equal to the total energy. So if we change this equation for a maximum, what you'll remember is that V max, or V naught, or V max, however you want to put it, is plus or minus omega x squared naught minus x squared. But obviously when V max is the case, that means x equals 0. So we can get rid of that value. Then square root of x squared naught, x naught squared is just going to be x naught. So we end up with V naught is equal to plus or minus omega x squared naught. That's the amplitude, remember. And then this equation now can become the energy total is equal to the half m omega squared, because we're taking this value here, x naught squared. And that works really nicely because that's telling us the total energy at this point, which is really, really nice. So for all intents and purposes, we can put all that back in. Oh, apologies, I've made a mistake. This isn't x squared, it's just x. And this isn't x squared, it's just x. However, it becomes squared when you come that way, come down that way. That was a mistake, but I'm back now. So we've got this equation. E total is a half m omega squared x naught squared. So we've got all of these values sorted out. Right, so where do we go from here? Well, what we can do from here is we can say, well, we need a term for potential energy. So let's look at this from the point of view of what we've got over here. If the total energy, E total, is equal to, at any point along this system, is equal to the potential energy plus the kinetic energy. It's got to be, because at any one point it's going to have some potential, it's going to have some kinetic. Obviously at the tops it's got the max potential and the minimum kinetic, and then vice versa for the equilibrium. But we can then use this to say that the potential energy is equal to the total energy minus the kinetic energy. Which, if we put these equations here together, we can find out something very, very interesting, an equation for the potential energy. So we can say that the E total, which is a half m omega squared x squared naught, minus half m omega squared x naught squared minus x squared will equal the potential energy. Well, actually now this becomes even longer. I'm just going to change colour. Half mx squared x naught squared minus. Now what you'll notice is that this we can expand and we can see what's going on here. Half m omega squared x naught squared minus half m omega squared x squared. Well, if you look very carefully at this, what do you end up with? Well, we've got this, apologies, this should be plus because it's it's minus the minus, so you get a plus when you put those two together. This minus this, well, those cancel, and that equals the energy of the potential. Well, that's a really easy equation. That's actually very similar to what we've got here. Energy potential is equal to a half m omega squared x squared. Well, it's very similar, but obviously we had quite a convoluted way of getting there. So the potential at any point on this is equal to the potential, and is equal to a half m omega squared times the displacement. Remember, this is the amplitude and this is the displacement. And this video just shows you where these equations have come from so that you can understand when and where to use them. In one of the next few videos, I'm going to give you an example of how we use all of these equations that we've done over simple harmonic motion, and we're going to link them all together in a question, and we'll have a go at how they can be used.